And welcome back. So we have the law of sines now, which holds for every triangle. The Pythagorean theorem doesn't, the traditional trigonometric ratios don't, but the law of sines does. Holds true for every triangle in the universe. So let's see what we can do with it. Let's go to town on this thing. Let's see what we can actually get from the law of sines. Right? Having a rule, having a tool is not great if you don't actually use it for something, because then it's just ornamental and worthless. So let's actually use it. Let's try and use the law of sines to deduce more information from triangle ABC here. And I'm going to go ahead and spoil this for you. The law of sines has a best case. It works best when you know two angles and some side. And let me show you why I mean what I mean when I say that. So for example, let's suppose I've got some triangle ABC. I know A side, literally, side A is 10. And then I also have two angles. Angle A is 60 and angle B is 45. So let's take the time to draw that out. I have a bit of a difficulty visualizing what I've got offhand. So here's my gorgeous triangle. This is pretty much the only general triangle you will ever see me draw. I draw it every single time. It is never to scale, and we can just deal with that. So let's see here. I've got a 60-degree angle. That needs to be degrees. I've got a 45-degree angle. And you know it's not to scale because this thing here has to be 75. And that's by virtue of the fact that every angle added together inside a triangle has to be 180 degrees. And so if you subtract 45 and 60 degrees out of 180 degrees, you end up with 75 degrees. So hey, that's one nice thing about knowing two angles. Not just for the sake of the law of sines, but for everywhere, right? Knowing two angles, you automatically get the third for free. That's not the case in general with knowing two sides, however. Unlike right triangles, where if you had two sides, you got the other one for free via the Pythagorean theorem, we no longer have the Pythagorean theorem, and so having two sides just does not automatically give us a third side. Not anymore. There's things we can do to get that third side, but it's not as automatic. That said, though, two angles, we automatically get the third straight away. Okay, now our drawing here is still a bit incomplete. I need to add the side length for A. Side A is opposite angle A, so 10 goes here. Perfect. So to find B and C, the only two remaining unknowns, and I'll go ahead and label that, B is opposite 45 degrees, and C, by necessity, is what's left. So to find our remaining sides B and C, I have to use the law of sines, which again is these ratios right here all being equal. I have the established ratio. I have an established ratio of 10 to sine of 60. So I'm going to use that along with either B over sine 45 or C over sine 75 to find B or C respectively. And we do that in two goes. We take two passes. First we find B using A to sine A equaling B to sine B. And then we will do it again, A to sine A equaling C to sine C, to find our remaining side. But once we have this set up, it really is just very basic, not even really problem solving at that point. You just multiply both sides by sine B, you get B equal A sine B over sine A, you substitute, you evaluate, and then if you need a decimal expression, you run it through a calculator. Exactly this one, we can find this one exactly. Sine of 45 is root 2 over 2, sine of 60 is root 3 over 2, 10 is, well, 10, and so all this simplifies to be 10 root 2 over root 3, or if you had to, 10 root 6 over 3, but however you slice it, it is about 8.16. So B is about 8.16. And again, we can't get C via Pythagorean theorem, so we have to use the law of sines again. And in so doing, we set A to sine A. I make an effort to always reuse previously given information as much as possible over things I find along the way. Technically speaking, you could set A sine A, you could set B sine B to C over sine C. Because we know B now, we know sine B, we know sine C. So you could do that, but that's an intermediate step. It's better just to go back to the givens and reuse those as much as possible. to avoid rounding error, compound error, things like that. In any rate, just take an established ratio, set it now to c over sine c, solve for c. And again, we'll get 10 sine 75 now over sine 60 degrees. And this together comes out to be 11.15, give or take. There is an exact measure for this, but we'll have to wait till after spring break, after the break, to get at what sine of 75 degrees is. That's not a nice angle as we have it so far. But there we go. That is the best case for working with law of sines. We've got two angles. We get the third one for free. So sine of A, sine of B, sine of C is known. And then you just use your one side length, your established ratio, to find the remaining sides. It's very direct, very straightforward. And if you look at all the writing we did, we had that line there, we had this line here, and this line here. We cracked the whole thing in just a few lines. Not bad. That's the good news. Here's the bad news. Okay, it's the worst news, actually. The law of sines only works when you have a ratio understood. You have to know A and angle A, or you have to know B and angle B, or you have to know C and angle C. If you don't have any full ratio, the law of sines falls apart entirely. So the side case, if you know all three side lengths, you do have a uniquely defined triangle. But the law of sines will not and cannot tell you what the interior angles are, no matter what you do. It can't do it. Period. There's another law, the law of cosines, that we'll dip into to answer this question, but we can't do it with the law of sines. And that's because if you look at these equations, right, if you pick these ratios right here, well, I know A and I know B, but I don't know sine A and I don't know sine B. I've got one equation, two unknowns. And if I pick these two ratios, pick this equation, I still have two unknowns in one equation. And I can't really highlight it, but if I picked A and sine A equal to C over sine C, again, two unknowns in that equation as well. There is no real definitive way of cracking that without doing an awkward system of trigonometric equations, and no, let's just not. So this is impossible using the law of sines. Not impossible period, but impossible for the context of the day. So too is it the case if you have side angle side. Because once again, that gives you, let me redraw this, let me trash this thing. So for some triangle, that's a triangle now, deal with it. This is why I only draw one type of triangle. We know this angle, and we know this side, and we know this side. And once again, I don't have a ratio on lock, right? I don't know this angle and this opposite side. I don't know this side and this opposite angle, and I don't know this side and this opposite angle. The law of sines, such as it is, we can't avail anything out of it. We can't use it to any avail. The law of sines has failed us here. So that's the worst news. It works great. It works almost effortlessly if you have two angles and a side, as shown here. It works awfully. It works impossibly if you don't have any angles or you only have one. Well, if you have side angle side. So that's the best news, that's the worst news, but I still have some bad news. So we'll get to that here in the next video. We'll get to the bad news in the next video. I look forward to it. It's going to be fun. Going to be fun. So maybe another quick question for you here. I'll see you on the other side.